Hi folks, welcome to section 3.3. In this section, we're going to start talking about increasing and decreasing functions, how we can find that from derivatives, and what that has to do with maxes and mins, because our ultimate goal in this chapter is still finding maxes and mins. Before we get into the calculus, I want to just review real quickly what we mean about increasing and decreasing. So a function is increasing means that anytime I have 2 points, A is the one on the left, B is the one on the right, then f of A should be less than f of B. And all that says in words is that the function is higher on the right than it is on the left. So it'd be like this first graph. Anytime I pick 2 points, doesn't really matter which ones, here's a point, let's make that look more like a point, here's a point, and here's a point. No matter which 2 points I pick on that graph, the one on the left is lower and the one on the right is higher. So that means it's increasing. It's moving up from left to right. And then decreasing is exactly the opposite of that. If I have 2 points, A on the left, B on the right, then f of A, or the y value for A, should be bigger than the y value for B. So that says the function is lower on the right. It's going down as we move from left to right. So the same kind of idea, if I pick 2 points on this line, the one on the left should be higher and the one on the right should be lower. That's decreasing. So the big question we're going to ask today, is what's the relationship between the derivative of a function and where it's increasing? And so this is a picture of an original function. F of x original is over here, and its derivative f prime is over here. So thinking back to some of the things that we learned in chapter 2 when we were talking about graphs of derivatives, on the first part of this original graph, my slope is negative, which means that on the derivative graph, I have negative y values. And then on the second part, the part going from the vertex down here moving forward, my slope is positive, which means I've got positive y values. So negative slope and positive slope are exactly, in this graph, decreasing and then increasing. So it seems like decreasing and increasing should have something to do with this positive and negative slope and positive and negative y values that we're talking about. And it turns out that they do. So by the time we get to the end of this section, you should be able to decide where a function is increasing and decreasing precisely, not just by looking at a graph and sort of pointing at points. You should be able to explain the relationship between the derivative f prime of x and increasing or decreasing. And we'll learn something called the first derivative test related to increasing and decreasing that helps us identify maxes and mins. So in this video, we're just going to talk about how do you find where a function's increasing and decreasing, and then there'll be another video for the first derivative test. So to summarize what we said back about derivative graphs, we said the derivative is positive where the function is increasing, or where the function is increasing, that means that its slope is positive. So the derivative is positive where the function's increasing, and then the derivative is negative where the function's decreasing, or where the slope is negative. So for these two graphs, let's think about which one's which. If I look at the first one, it has a positive slope, and then a negative slope, and then a positive slope again. And that looks like what we see going on here. It's got a positive y value, a negative y value, and then a positive y value. So this one is my original, not prime, original f of x. And this one is my derivative. So when we have a positive slope on the original, so that would be that part and this part, that corresponds to these two parts of the derivative graph that have positive y values. And where we have a negative slope, that corresponds to this part of the derivative graph where we have negative y values. So we're going to use that idea to write some equations that will help us figure out more precisely where is the function increasing and decreasing, instead of just being like, well, until here and until here, because that's not really precise. So here's the theorem we'll be using. As long as we have a continuous function that is differentiable, we need to be able to calculate its derivative in order to be able to use it, is all that's going on there. If the derivative is positive on some interval, then f will be increasing on the closed interval. If the derivative is negative, then f will be decreasing. And finally, the one we don't see very often, but it does come up, if the derivative is 0 on an entire interval, then the function would be constant on that same interval. So the relationship is when the derivative is positive, f is increasing. If the derivative is negative, f is decreasing. And if the derivative is 0, then f is constant. Now it's really important that in this last one, we mean that f is 0 on some interval, not just at a single point, because constant at a single point doesn't really make sense, but constant on a whole interval does. So here's the procedure we'll use. We want to find where f is increasing or decreasing. We'll start off by going back to section 3.1, finding all the critical points, both the 0 ones and the ones that it doesn't exist. Once we have those, we'll use those critical points and any places where the function doesn't exist to split up our interval into some smaller subintervals. And then the idea is essentially that you pick any point you like inside each of those smaller subintervals, and you decide whether the derivative is positive or negative at that point. So it would look something like this. If this number line represents the domain of my function, maybe I have a critical point 1 and a critical point 2. And so those two critical points have split my number line up into 3 distinct sections. And what we want to do is decide whether our function f prime is positive or negative on each of these sections. Well, the only place that f prime can change from positive to negative is either at a critical point, that would be like where the graph crosses the axis and it changes from positive to negative, or at some place where it doesn't exist. If I have like a vertical asymptote or something, then I could change from negative to positive, moving across a vertical asymptote or something like that. So that'll be the idea. Let's just do an example and get going with this. We want to decide where the function is increasing or decreasing. First thing we need to do is find the critical points. Well, in order to find the critical points, I need the derivative. So my derivative for this function is going to be 3 times 1/3 is just 1x squared minus 1. And so for critical points, that means we have to do 2 things. We have to figure out what makes x squared minus 1 0. And if there's any places where x squared minus 1 doesn't exist. So x squared minus 1 equals 0, you could do one of 2 ways. You could factor it, or you could just move the 1 over to the other side. Take square roots. As long as you remember that anytime you take square roots of both sides, you have to put a plus or minus, because there are 2 numbers that are squared to equal 1, be positive or negative 1. So here's 2 of my critical points, positive and negative 1. And are there any points where this function, this derivative, doesn't exist? Well, no, it's just a parabola. It exists everywhere. So here goes my number line. And the only numbers I'm going to put on here are my critical points and any points where my original function doesn't exist. I don't have any trouble with that in this one because it's just a polynomial. It exists everywhere. So I've split my number line up into 3 separate sections. And I know that the only place my derivative can change signs is at 1 or -1. So that means whatever sign it has, positive or negative, on this interval, it must be the same sign on the whole interval. And the same thing in between -1 and 1. If it's positive the whole time. If it's negative the whole time. It can't be both. So the magic of that is we get to pick any number we like to be a test point. So for example, I might pick -2 for this first interval, because that's a number inside this last part of my number line. I might pick 0 for the middle interval, and I might pick 2 for the third interval here. The only thing that's important is that you be sure that you pick an x value that's inside the interval and not one of these endpoints. We don't want to use our critical points again. We want to use some different x values. And then all we have to do is plug that number into our derivative f prime and see whether it's positive or negative. So if I plug in, for example, -2 to my derivative, that's going to end up being -2 squared is 4, -1 is 3. So that means that I have a positive derivative on this first interval. If I plug 0 into my derivative, 0 squared minus 1, that's going to be -1. So my derivative is negative here. And then finally, if I plug in 2 to my derivative, so that's just 2 squared minus 1, which is 3 again, and that's positive. So I don't even really care what numbers these are. I just need to know whether it's positive or negative. So what does that tell me? Well, it tells me something about increasing and decreasing. Because if the derivative is positive, that corresponds to the original function is increasing. And if the derivative is negative, that corresponds to the original function is decreasing. So we have for f, this was for f prime, positive and negative. The original function is increasing on 2 intervals, this one and this one. And so those 2 intervals are -infinity to -1 and 1 to infinity. And then, running out of room here, y'all. F is decreasing on the interval from -1 to 1, because that's where our derivative was negative. So you see how I'm building these intervals. The 2 critical points are always my endpoints. So this first section of number line goes forever to the left and ends at -1. That's where I got this interval from. The middle section is from -1 to 1. That's this one. And then the last section starts at 1 and goes forever to the right. So that's this 1 infinity. So we just found our critical points, put them on the number line. We picked any test point we like as long as it's inside each of the intervals, and plugged it into the derivative. That answer told us whether the derivative was positive or negative, and then we just had to translate positive and negative into the original function being increasing and decreasing. Let's do another one. Let's decide where this function is increasing and decreasing. Well, before I can decide where this function is increasing and decreasing, I got to know its derivative. And this is a quotient, so I'm going to have to use a quotient rule. My u is x. My v is x minus 2. And so u prime is 1. V prime is also 1. And then putting it all together says that the derivative is u prime times v, so 1 times x minus 2 minus u times v prime, so that's x times 1 over v squared. And we'll simplify that just a little bit. That's just x minus 2 minus x over x minus 2 squared, and then the x's cancel. So we have negative 2 over x minus 2 squared. There's our derivative. Now the whole reason we needed a derivative was so we could find our critical points. So that means we have to figure out negative 2 over x minus 2 squared. Can that equal 0? And negative 2 over x minus 2 squared doesn't exist. I also want to point out that way back here in the original problem, we need to make ourselves a note that x cannot equal 2, because if it did, we'd have a 0 in the denominator. So 2 is the only number that's not part of the domain of our function. So we will put 2 on our number line, because this graph will have an asymptote there, but it cannot be a critical point. So let's see. For this one, if we tried to solve it, the thing we would do would be to multiply both sides by x minus 2 squared. And let's see what that would look like. I would multiply by x minus 2 squared. I would multiply by x minus 2 squared. These would cancel. But now my equation says negative 2 equals 0. And so that makes no sense at all. This one has no solution. However, it's a fraction, so there are definitely some places where it might not exist. And that would come from making the denominator 0. And that would say x equals 2. Oh, but wait, we said x could not be 2. So this one is not a critical point. I'm going to start abbreviating critical points because we're going to say that a lot. This one is not a critical point. However, it still does go on our number line because it's a place where the function doesn't exist. And in fact, that's the only thing that goes on our number line is 2. Because we have no critical points to put on here also. So what does that mean? That means we've got 2 sections on our number line, and we need to pick x values. You can pick any x's you like. I like 0 because it's really easy to work with. And then from this other section, maybe I pick x equals 3. So for both of them, I need to find the derivative at that number. So f prime of 0 would be negative 2 over 0 minus 2 squared, which would be, negative 2 over 4. And I don't even really need to simplify that. I just need to know that that's negative. So my derivative, f prime, is negative on this first interval. If I plug in 3, I got negative 2 over 3 minus 2 squared. That's negative 2 over 1. That is still negative. So let's translate that back to something about f being increasing or decreasing. F is increasing. And then where is f decreasing? Well, increasing would mean positive derivative, and I don't have any positive derivatives, so f is not increasing anywhere. F is increasing nowhere, and f is decreasing from negative infinity to that's not a negative 2, sorry y'all. Negative infinity to positive 2, and from positive 2 to infinity. And if you take a look at the graph of this equation, that's exactly what you should see. It has an asymptote at 2, and it will be decreasing on both sides of the asymptote. one more example of the increasing and decreasing. This time let's do a trig function. Same deal as usual. We need to find the derivative in order to find some critical points. So this derivative is actually a chain rule. So we need an inside and an outside. The inside is 3x, and then the outside would be sine u. So that means that our inside derivative is just 3, and our outside derivative is cosine u. And when I put all of that together into a final derivative, I get 3 times the cosine, and I'm going to replace this u with my inside. So that was 3x. All right, so then we think about some things. What numbers would make 3 cosine 3x equal 0? And are there any places where 3 cosine of 3x doesn't exist? Well, first let's get rid of the 3 out in front by dividing both sides by 3. So then this looks like cosine of 3x equals 0. And we'll just go ahead and add another page here because I know I'm going to need it. So the places where cosine has a value of 0 are pi over 2, 3 pi over 2, negative pi over 2, things like that. So that's going to mean that 3x could equal pi over 2, it could equal 3 pi over 2, could equal 5 pi over 2, or it could also be negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, so on and so forth. All right, well, if those are, all of those make potential equations for 3x. If we wanted to get x by itself, then we would have to divide by 3. And so when I divide by 3, that's going to give me pi over 2 divided by 3 is the same thing as pi over 6. The reasoning behind that, if you need to see one, is that pi over 2 divided by 3 is the same thing as pi over 2 times 1 over 3. And so I just multiply the pi's and the 1 and the 2 and the 3. So I get pi over 6. And so similarly, all these other ones would also do something similar. This would be 3 pi over 6. This would be 5 pi over 6. And then I would have their negatives also. Negative pi over 6. Negative 3 pi over 6. Negative 5 pi over 6. All right, so those are our critical points from this side. Ooh, there's several of them. Any places where cosine doesn't exist? Well, no, cosine exists at every angle because its graph doesn't have any asymptotes or holes or anything like that. Now, we only want to talk about numbers on the interval from negative pi to pi. So that means that although I wrote these ... dots, we don't actually need to go any bigger, because if I go any bigger, I'll get outside of that interval negative pi to pi. So let's try to put this on a number line. If you think about what the graph of cosine looks like, you're going to expect it to increase and decrease back and forth a lot. So let's see, I've got, negative 5 pi over 6, negative 3 pi over 6 is the same thing as negative pi over 2, y'all. Negative pi over 6. I've got positive pi over 6. 3 pi over 6, same thing as pi over 2. And then I've got 5 pi over 6. So that's a lot of intervals we got going on here. 1, 2, 3, 4, 5, 6, 7 intervals. And we're only talking about negative pi to pi. So although we're used to drawing arrows, we've really got endpoints happening right here at negative pi and pi. So if we want to know where our function is increasing or decreasing, then we have to pick points in between, one point inside each of these intervals. The easy one is probably right here, x is 0. And then let's see, what about the next one? Pi over 4 is pretty easy to find cosine of. It's on the unit circle at least, and it's between pi over 6 and pi over 2. And then maybe I would do 3 pi over 4 and negative 3 pi over 4. And then for these last ones, we'll use pi because pi is included as one of our numbers. The endpoints of our interval are included, and pi is a nice easy number to work on. So I got to find the derivative. Remember, let me recopy our derivative down here so that we don't lose track of things. Our derivative was 3 cosine of 3x. And so if I wanted to find, say, f prime of negative pi, this is one of those situations where you might want to make use of Desmos and make yourself a table where you can put in all these x values and let it tell you the y values. Now, all you really care about is whether this is positive or negative. And so if you plug in negative pi right here, you should find out that the cosine of this will be negative 3 pi will end up being negative. What you should come out with here is that f of negative pi is negative 3. What about if I do negative 3 pi over 4? Well, I'm going to plug that in for x right here. And again, I don't really care what my answer is. I just care that if I put that in my calculator, the answer is positive. What about negative pi over 4? If I put that in here for x, be sure your calculator's in radians. And I put 3 cosine of 3 times negative pi over 4. Then I find out that that cosine and that answer is negative. If I put in 0, 0 is the one that's easy to do in your head. The derivative at 0, cosine of 0 is 0. No, cosine of 0 is 1. So that ends up being 3. And it turns out, as you keep plugging in each of these x values in for x, that the pattern continues. It keeps alternating. Now this is a really common pattern, but keep in mind that it doesn't always happen, and you really do need to check either by making a table with all of these or by plugging them into your derivative one at a time and finding their y values. So to sort of summarize all this and change it back to talking about f, f is increasing on some intervals. It's increasing from negative 5 pi over 6 up to negative pi over 2. It's also increasing from negative pi over 6 to pi over 6. And it's also increasing from pi over 2 to 5 pi over 6. Those are all the places where we had positive derivatives. Well, then the decreasing must be the other ones. So we were decreasing on the interval from negative pi. I don't know why I cannot write 5 pi over 6 right, y'all. Negative 5 pi over 6, we were decreasing. We were decreasing from negative pi over 2 to negative pi over 6. Also from positive pi over 6 to pi over 2. And finally from 5 pi over 6 to pi. Notice that because the pi's are included in our endpoints, they got brackets. Everywhere else we put parentheses. Quite honestly, the subject of whether you use parentheses or brackets for increasing and decreasing is not widely agreed upon. So I will accept either one. If your homework tells you to do it a particular way, then please pay attention to that. But for our purposes, on a test, on a quiz, I will accept either one of them. There are many more important things to worry about here than whether you're using a parentheses or a bracket. Much more concerned that you have the right intervals for increasing and the right intervals for decreasing. All right, so that one was a little bit long, but it was just because it had a trig equation that had a lot of solutions, and that gave us a lot of intervals. But if you think about what the trig graph looks like, think about what cosine looks like. It changes from increasing and decreasing back and forth a lot, so that matches up with what we might expect. Now, I am aware that these problems take a little bit more time, and I am not going to put 5 of them on your test. But I am going to put 1 of them on your test, and just be aware as you're planning for your homework that this is the kind of thing where it's just going to take some time to practice, and so plan accordingly. All right, so that should take care of our increasing and decreasing. We always find the derivative, find our critical points. We put them on a number line. And then we pick any numbers we like in between, inside each interval, and plug them into the derivative to see whether it's positive or negative. Finally, we change our positives and negatives to increasing and decreasing for f. In the next video, we'll talk about how we can use this idea together with the first derivative test to find maxes and mins.